So this is based on a journal paper that came out at the end of last year and will be published eventually this year in transaction of the Moscow Mathematical Society. And it's going to be about double rotations, but before talking about double rotations, I want to go a bit back and talk a bit about, well, I mean, rotations and interval exchange transformations. Even though probably the majority of people in the audience know this, I think it's a nice introduction to double rotations. And the idea is for this talk to be a bit informal. So, I mean, if you want more details on the proof, I'm happy to give more details, but the idea is more to give an introduction to the subject, because I think that there is a lot of open questions in this area. So it's kind of, think of it as an advertising, so that maybe, you know, if you're interested in some of these questions, then, you know, you are welcome to join us and try to prove some of them. So that's why the idea is to be a bit more gentle than maybe the usual seminar. So of course, everybody knows rotations, which are probably the simplest or one of the simplest dynamical system. And so rotation are alpha of the circle S1. It's simply, you know, if you take your circle and you rotate by an angle alpha, so maybe you rotate by, you know, this amount. Say that this is your alpha. So you just rotate counterclockwise by the angle alpha. Of course, we can use the fact that S1 is a quotient of R modulo Z, and recalling this, we can open up the rotation on the unit interval. So this is the same of R modulo Z. So we can identify S1 with 0, 1. And on 0, 1, the rotation just becomes a much simpler transformation, which can be seen as an exchange of two intervals. So I just have, this is my interval 0, 1, and then I have, I don't know, I take here, this is 1 minus alpha. So what I do is that if this is 0, this is 1, and maybe I already forgot which color I picked. So this interval here gets sent to the beginning interval from 0 to alpha, and then the remaining portion goes to the remaining portion of the interval. Okay, so it's, intervals that have the same color goes mapped by a translation one to the other. So with this respect, then R alpha, it's simply taking x and adding alpha, and then taking modulo 1, so the fractional part. So a natural generalization of this is, instead of taking two intervals, taking a different number of intervals, I don't know, 3, 4, 10, your favorite natural number, cutting the interval into this number of pieces and then rearranging them. And this is called interval exchange transformation, and was introduced in the Soviet Union in the 60s, and then shortly after in the US. And my understanding is that it's not exactly clear who introduced it first, and there's a lot of people that claim to be the first, so I don't want to dive into the history, but, you know, I mean, I don't want to pick sides. So if some of you know the history more or some reference, I would actually like to read a bit more about it, but, you know, bear with me for not being more explicit. So IETs, there are interval exchange transformations. So this is pretty long to write, so I will always write IETs. Consists exactly in what I said. So what you do is that you pick your interval. Okay, this was a bit squiggly. And then I divide it into 4 pieces. I don't know, something like this. And maybe A, B, C, D. And then what I do is that I rearrange them by a translation, so that after translating them, I still get a partition of the interval. So I do not allow translations that would overlap the image interval. Okay, so I don't know, maybe this interval D goes to the beginning here, and the one with C goes like here. Then I have a longer one, which is B, and this is A. So I mean, I don't know if they are exactly the same size, but approximately. So what I do is that I simply translate this interval A here, this interval B here, etc. Okay. And the important thing is that I start with a partition of my interval, and I end up with a different partition. Okay. So they can be described by giving the length of the intervals on which I'm subdividing my bigger interval, and then on the combinatorics. And it turns out that it's convenient to actually give names to the intervals once and forever. And so I have two permutations. One that tells me how are the intervals at the beginning and how are after the transformation. This may seem a bit redundant, but actually turns out to be really useful in the theory. So I have a permutation by 0, which in this case would be A, B, C, and D. I have a permutation by 1, which in this case is D, C, B, A. And then I have length of the intervals. So I have a length vector, lambda. And this is, in this case, it has 4 entries. But actually, usually what you ask is that your interval is of length 1, so this lives in the simplex. So usually one asks that the sums of the lambda alpha is equal to 1. And this is not incredibly important. But, so interval exchange transformation have been studied a lot from the introduction from many different perspectives. And they are an interesting example of a parabolic dynamical system, or a system that has some amount of chaos, but not as much as an parabolic system would have. And they are connected with topics in foliations and surfaces, and dynamics on something called translation surfaces. So they have been studied a lot from many different perspectives, and we know, well, I don't want to say everything, but Sasha gave us a seminar about this and said that we know about almost every property that happens on almost every translation interval exchange almost surely. So this is somehow the case. So what we know, for instance, let me just say a few things. So we know that ITs are generically minimal, meaning that if I fix one permutation data and then I pick at random some lengths, then with probability 1, I get a transformation which is minimal, meaning that every orbit is dense. And this was proved by Keen in 1975. Then we also know that generically they are uniquely ergodic. This was called Keen conjecture and was proved independently by Mazur and Veitch at the same time in 1982. And their papers came out one after the other in the same volume of annals. And the proof is completely different. They use completely different techniques, and actually for our talk is much more relevant the proof of Veitch. And also we know that generically they are weakly mixing. And this was proved by Avila and Forni in 2007. And we know that they are never mixing. This was proved much earlier by Anatol Katok in 1980. So why I'm saying this? Because many of the results for interval exchange, and a few of these actually, have been proved using something called Rosi-Veitch induction. So many results have been proved. Using Rosi-Veitch induction. So what is Rosi-Veitch induction? I will give you an example. I will not give the formal definition, but the point is to take the restriction of the IT on a subinterval of the original interval, chosen in a way that the transformation induced on this smaller interval is still an IT and still on the same number of intervals. So we don't want to increase the number of intervals, so the complexity, the combinatorial complexity doesn't increase. Okay. So maybe, I mean, we will use an induction like this. So maybe let me spend a minute commenting about it. So maybe let me copy this. Let me give an example. So what you do is that you look at the last two intervals. So you look at the last interval in the starting, the starting configuration, and the last interval after applying the transformation, and you look at which one is longer. So in this case, I mean, they are almost the same, but in this case, this interval is a bit longer than this other one. So in this case, you say that D, so since the length of D is greater than the length of A, then D wins and A loses. And what you do is that you cut the interval, I mean, this interval here, you cut it from here. So you remove this interval. And what you do is that you still have an IT, because basically the points that belong to A, now they get mapped outside the interval, but they land in D. So after applying twice in your original map, you will actually end up here. So now this is my D, it goes here, and this is A. Okay. So far, so good. Questions? You can also use the chat if you want, because I have it open. So if you don't want to open your mic, you can put questions in the chat. I'll try to answer. Of course, it could also happen the other way around, and basically you do the same. Now I don't want to go into the details, but the interesting point is that you have an algorithm that tells you once you have an interval exchange transformation, you can produce a new one with the same combinatorial complexity. And you have some rules that tells you how the two permutations that define your interval exchange change after applying induction. And there is also a way in which you can write, you can write the original lengths of your interval in terms of the new ones, right? Because what I've done is that basically the interval A, C, and B have the same size. And what I did is that I subtract from the length of the interval D, the length of the interval A. So all the length of the interval A, B, and C stays constant, and the one of D gets, decreases exactly by the amount lambda A. So what I can do is that I can write a matrix that is a non-negative matrix, and this will be extremely important, as non-negative such that the lengths lambda before I apply the induction, they are maybe in matrix A, such that, okay, maybe A is not the right letter, maybe V, such that is V times lambda prime. Okay. And the fact that it's non-negative is really important, because basically you can prove that if you didn't pick very badly, for this one, this matrix eventually, when you take longer and longer iterations of the induction, they will become positive, and then you can apply Perron-Frobenius arguments. So for instance, the proof of unique codicity by Vich goes along this direction. Of course, there's much more, but one of the key points is exactly showing that this matrix eventually become positive, and then you can study the projective action on the space of measures, and you show that this is contracting, and so in the limit you get only 1 point, which is your uniquely ergodic measure. Okay. The other thing that I want to say is that there is a finite graph a finite directed graph. So, which encodes how the combinatorial data, meaning those two permutations that give you your interval IT, your IT, combinatorial data changes under Rosi induction. Okay, this will be relevant later. Okay. Okay, so this is all classical. It's been studied a lot by many people, and I'm sure that the majority of people in the audience probably know this better than me. So thank you for your patience. Now let's go into the setup of our talk. We do not talk about interval exchange, but actually what we did in our paper was study a more general class of transformation, which were introduced in 1994 by Boschernitz-Hahn and Kornfeld, which they called interval translation mappings. Okay, so in 1994, Boschernitz-Hahn and Kornfeld defined interval translation mappings. So it's almost the same word, but instead of exchange, I've got mapping, and this makes a lot of difference. And so again, this is very long, so I will just call it ITM. And the idea is similar. So I have an interval, say of size 1. I chop it into finitely many pieces, and then I translate them. So what's the difference is that now I do not allow, I do not ask for the images of the interval to still form a partition. So I allow for overlaps, okay? And actually, not only overlaps, the images can also be disconnected, okay? So the image of the whole interval can be disconnected. So it's something like this. You know, I take one interval like this, and I say that I divide it into 3 pieces. I will use something like this to make the drawing. And then what I do is that I don't know, maybe I'll move this one here. I move this one here, and then this one here. Okay, maybe it's very too small, something like this. Okay, so I allow to have overlaps, and so I will have gaps, and also I can have, I mean, the image can be more than one connected component. Okay. Okay. So this increases by a lot the complexity of the space, and actually, I don't know, maybe one way in which you could parameterize this is, you know, giving 3 lengths and then 3 translations, for instance. So this already has a much bigger dimension. Questions? Clear? Okay. So already in the paper by Boschernitz and Kornfeld, they noticed, they observed that an ITM can have 2 different behavior. Okay, so ITMs can be either of finite type or infinite type. Okay. So what do I mean by this? Since my image of the starting interval need not to be the whole interval, actually this is kind of the interesting case, then I can look at the attractor. So I can define omega k to be the intersection of the beginning interval with the image of that under my translation, under my map, and then square, etc., until k. And then 2 things can happen. If there exists an n such that this attractor stabilizes at step n, this in particular means that my attractor is it's a collection of intervals. It's a finite collection of intervals inside, and there's finite but positive back measure. Then in this case, I can restrict. I will say that the ITM is of finite type. So in this case, the T is of finite type. And moreover, if I look at the induced transformation of the original ITM on this attractor when it stabilizes, this is an IT, okay, on some number of intervals, which, I mean, I don't think there is a closed formula for this, but I mean, you can sit down and try to compute it in your favorite example. And then if this doesn't happen, meaning if this attractor keeps shrinking and it never stabilizes, then in that case, you never stop, and in the end you get a fraction, like a Cantor set attractor. And in that case, you would say that your ITM is of infinite type. So if does not exist an n such that omega n is equal to omega n plus 1, then T is of infinite type. And if I take the intersection over all n of the images of my interval is a Cantor set. Okay. So in the same paper, Boschenitz and Corfield made the following conjecture regarding which behavior they expected to be the typical one. And I don't know, maybe it's somehow it's bad news, but I mean, this is a fact of life. So the conjecture is that the set of parameters yielding infinite type ITMs as 0 Lebesgue measure. So basically, if you pick, I don't know, 10 intervals at random and you translate as you want, then you expect this to be of finite type. Okay. And to the best of my knowledge, this conjecture has been proved only for the for interval distribution mappings on 3 intervals, which is exactly the class we will talk about today. I mean, it's more or less the class we'll talk about today, which is double rotation. Okay. And if you take 2 intervals, it's easy to see that on 2 intervals you always get a rotation. Not even an IT, always a rotation on the finite type attractor. Okay. Okay, questions, doubts? Okay, now let me define double rotations and let me tell you what was a bit of what was known and then what we proved. So we study double rotations, which are basically the simplest example of ITMs, which are not rotations, which are not ITs. The simplest example.
Mauro, I have a question.
Sure.
Did they conjecture anything about Hausdorff dimension?
No, but you are spoiling my result.
Sorry.
No, you're welcome. So what we prove is that in case of double rotation, is Hausdorff dimension lesser than 3, which is the ambient space. So it's really, and there are some simulations which tell you that they are like around 2.5, I would say, between like 2.4 and 2.64, something like this.
Nice, thank you.
Oh, you're welcome. Okay, we study a simple example of ITMs, which are double rotations. So what are double rotations? Well, you can see it on the circle.
Sorry if I interrupt, but in comparing this Hausdorff dimension, comparing with those with flips, like ITs with flips, where there is this Sasha's or other works with, there the Hausdorff dimension is 0 or it's also, no, it's also intermediate between full and 0.
I'm not 100% sure. I think it's
those
intermediate.
Don't have periodic, but
I think it's intermediate. I think also that the proof is, I mean, if I remember correctly, the proof it's basically uses this Avila de la Croix estimate.
I see.
So I think it gives you just, just the fact that it's, it only gives the fact that it's smaller than the ambient space.
Sure, I understand, but it's presumably positive also, yeah.
I think it's expected to be positive.
Yeah.
But
there's no result where it's been, no way, we know. Something has been computed. The one of this famous fractal Rosi gasket, Sacha, Pascal.
Yeah, the Rosi gasket, there is an estimate from, there are plenty of numerics. And also there is a paper by Gutierrez, Romo, and Mateus. It's a very short paper, and they do like a rigorous computation estimate from below, which is 2 point something, but I don't remember.
Okay, great. Sorry, thanks.
Okay, so double rotations. Let's go back to the definition. So you could see them on a circle, or you can see them in an interval as you wish. And what you do is that you cut your interval in two pieces, and you rotate one by some amount and the other by a different amount. Okay, so you have three parameters basically: where you cut and the amount of translation of the two. So it's something like this. So I take a transformation from 0, 1 to 0, 1, and what I do is that I take my number and then I move it by an amount alpha if y is lesser than a number c that I pick, and I move it by a number beta if y is bigger than c. Okay, and here alpha, beta, and c are three numbers in 0, 1. So maybe let's pick the open interval because 0, 1 is not really interesting. So double rotations were defined precisely like this in a paper by three Japanese. So they were introduced or if you prefer the word singled out, by Suzuki, Ito, and Aihara. And they studied a bit this class, and they introduced a renormalization on this, which is somehow reminiscent of Gauss map on real numbers. So they introduced Gauss, maybe like Gauss like renormalization procedure. And they proved some intermediate result toward the conjecture, and then Hank Bruin and a student of his called Black, they proved some years later in 2012, using this induction, that the conjecture is true for double rotation. Okay. Okay, so what do? We refine this statement as I spoiled it before, and show that not only it has zero measure, but actually is small in the sense of Hausdorff dimension. So it's the dimension of this is strictly smaller than 3, which is the ambient, the space of parameters. And okay, let me write this and then I'll comment a bit on the statement. So this is Artigiani, Fougeron, Skripchenko, and it will come out this year. So the set of parameters yielding infinite type double rotation as Hausdorff dimension lesser than 3, strictly less than 3. Okay, so to prove this result, we proved it in a quite different way from the way in which Bruin and Clark proved the result, and we introduced a new renormalization, which is much similar in spirit, is to the classical Rosi induction. So we are able basically we define this new induction, we show that it has some nice property, and then we show that this new induction fits into formalism that has been called simplicial system, which has been studied a lot by one of us, by Charles Fougeron, that has a really fantastic paper that came out a couple of years ago on the arXiv about simplicial systems, in which basically he refines the approach by Kerckhoff to the proof of uniquely ergodicity of IETs, and some insight given by Avila, Gusera, and Yukos in their famous paper about exponential mixing for the technological flow. And with these techniques, he proves a lot of general statement for some simplicial systems that then can be applied to many multidimensional fractional algorithms. And so what we do is that we basically show that this new renormalization, which is not that easy to define, once you are able to produce it, and show that it's well defined, then this renormalization fits inside the multidimensional fraction algorithm, framework that Fougeron developed, and we're able to prove many results using these general results somehow. So maybe I'll write a few words about this. So we introduce a renormalization closer to the Rosi one, and exploit Fougeron work on simplicial system. And just to give a word about what simplicial systems are, it's basically something that looks like Rosi induction. So it has a finite direct graph, and at every vertex of the graph, there are some simplices or some spaces like that behave like simplices, and then you have maps from when you have an arrow from one vertex to another of the graph, then you also have a map from one simplex to the other. And then of course you have to study much more, but you show that if your system is not too degenerate, you can prove a lot of interesting properties. So after this, we also exploit Shah's work to do the following. So we obtain using some thermodynamic formalism, we obtain a measure mu, which is invariant under our renormalization. And we show that with respect to this measure, then almost every double rotation is uniquely ergodic. Theorem with the same authors. So mu, almost every double rotation of infinite type is uniquely ergodic. And let me say that this was proved conditionally by Bruin and Gluck, meaning that they used some different thermodynamic formalisms to show that if there exists such a measure, then this should hold. But they didn't know whether such a measure existed or not. So it was, and we show that this measure actually exists, and this is obtained by taking the suspension of our system and consider the measure of maximal entropy there, and then projecting it downstairs. And finally, the last corollary we get using this result plus a very recent work of Serge Trubetskoy is that double rotations are almost never weakly mixed. So mu, almost every double rotation of infinite type is not weakly mixing. Because basically what happens is that Trubetskoy in his recent work showed that almost every double rotation, so if there is an invariant measure, almost every of these is not weakly mixing. I mean, it admits, so sorry, no, let me say it differently. So it shows that if you take a double rotation, then they always admit a non-weakly mixing measure. And then if you only have one invariant measure, that has to be not weakly mixing. Okay, sorry, I made a bit of a mess, but I hope that the second time was clear. Okay, questions on the statements? Okay, so let me give you some elements of the proof, and then I'll see if there are more questions. So elements of proof. So somehow we, the first step is to pass from double rotations to 3 ITMs. So this is something that Dennis Vogt noticed before, and when basically 3 ITMs are the same of double rotation, even though they look slightly different classes, they are basically the same class. So reduce double rotations to ITMs on 3 intervals. And then when you have ITMs on 3 intervals, you can introduce a simple Rosi-Vincha induction, basically doing exactly what I explained to you before. And this, if you're a bit careful but not too much, you can show that this is well defined and you don't increase the number of intervals.
What does it mean, reduce? So can you give a sense of what reduce?
Yes. It's so it's basically once you ask, so you have a double rotation, right? So the interval in images, you ask that okay, I'll do a drawing. So you don't want something like the drawing that I had before. So I don't want the beginning of the interval or the end to not be covered. So I can simply shrunk there. And after I do that, I can always I can basically give different names to the intervals, and I can represent my double rotation to a 3 ITM.
And the overlap? What do you do with the overlap?
No, the overlap will remain because it's an ITM. I'm not. It's not an IT. Yes. So the overlap remains, but the point is that
is there formally some kind of semi-conjugacy or something? Can you think of this double? No, it's not. Is it some?
No, it's simply.
It's not simply, a blow up or something.
No. It's nothing complicated. It's simply restricting like to the image basically. It's like taking the second power, third power, something like this. It's just an induced map on a subinterval. It's nothing more complicated than that. Because the point is once you exclude once the intervals you have get mapped to the border of your interval, then the trick is that you only have one of, the overlap.
Yes.
Is exactly the size of the hole. And then this allows to move back from double rotation to 3 ITMs. This simple observation allows you to do the
so instead of having an overlap in a hole, you think of having an interval of a 3 IT there.
ITMs. No, ITM. No
ITM. Sorry. ITM. Okay.
No. Sure. Yeah.
Okay.
No, otherwise, because if I had an IDT, then I would be done. This would be of periodic type, of finite type.
Oh, sure. Okay.
Okay, and so one can then do simply Rosi kind induction simply by cutting, basically doing the same game of before. I look at the left, the rightmost interval and look at which one is bigger and cut there. And this is simple to define, but it has a big problem that when I define this Rosi induction, I have 2 kinds of parameters. So I have Rosi, let me call Rosi like induction, which we denote by the letter Z, standing for Zurich for a reason that I will explain in a sec. And the problem is that in my description of 3 ITMs, parameters are 2 different types, because I have the lengths of the interval and then I have the translating vector. So I have parameters describing ITM are lengths plus a translation. Actually, you can pick parameters carefully so that you only need one. And the problem is that under the renormalization, this transform with a non-negative matrix. But this one transform with a negative matrix. And so basically, I mean, all our machinery breaks down. So you need to be a bit more smart. And you need to have a better idea. And the idea is to somehow try to pretend that the ITM is actually an IT. So what you do is that you increase your combinatorial complexity. So you pass from 3 intervals to 5 intervals. And when you have 5 intervals, you can pretend that your transformation is an IT. And maybe I'll show in a drawing, and I'll try to explain a bit better. So I have my intervals here, something like this, and this, and then I have this, and then I know maybe I move this here, and let me put this here, and then this here. And what you do is that, as I said before to Corinna, so since I reach the beginning and the end of the interval, then this allows me to say that the overlap is the same of the whole. It has the same length. So now what do I do is that I can cut this one here and cut this one here, and so and do this. So now I will have, I don't know, maybe I should give, okay. So then I also cut it in the beginning. So I have something like this, and then I have this, and this one is like here. And so what do I do? So now I have this called A, B, C, D, sorry, B, C, and D. And these 2 intervals, they are exactly the ones that overlap. So they have the same length. So I'm allowed to give them the same name. And then I can code this as B with an underscore, saying that this is my whole. This is A, this is B, and this is C. And so what the fact, these 2 intervals that have the same name, they get mapped to the same part. And so now I can write this in a fashion similar to IITs. So I have something like this. I have A, B, B, C, D, D, B, A, B, C. Okay. And now, of course, now I have this whole, so I have to treat it a bit more carefully, but I can define a different
So, sorry, on 5 ITs you have one relation essentially. No, this is a relation.
Well,
B
this
equal
is
to B bar.
Yeah, but this is not
no.
So B is equal to B bar, yes, but this is not exactly on 5 intervals because these 2 have the same name somehow. So this is not exactly, I mean, this is not exactly an IET on 5 interval, right? Because you have to have twice the letter upstairs.
But
and then
what does it mean? It's the same name. It can be marked, right?
Yeah, okay, I could be marked, but then you know, I have, okay, this depends a bit on your taste, but the point is that I should have one letter repeated twice upstairs, and then the same letter should be once downstairs without a mark, and then with a mark that we put the underscore. So not, you know, you cannot have like 3 times the same letter, for instance, or something like this. Does this make sense?
Yes, but still one of the B was B bar already before. One is the pre-image. Why do you give them BB and not BB bar already in the first row?
Because these 2 intervals that have the same name B, they go both of them go here.
To the same. Okay,
to the
okay.
same.
So sorry. Yeah,
And this is empty. Nobody goes
I
there.
see. I understand.
So that's why I need, to specify that this is the whole somehow. This is my special. This is the whole, and then these two, they go here.
But after this, the B becomes normal. The whole stays a whole, but the B, which is not barred, you forget that it was special.
Yeah, I mean, the only, you forget it was special in the sense, I mean, basically, but this allows you to say, if you have your interval here and here, they go to the same place.
I understand.
So this is somehow how you record this. Yes, I think I'm running short on time, so let me just say a couple of more words and then I'll stop. I just want to say that you define a new induction, which is still something like Rosi Vincha, but now 5 intervals, taking into account the fact that the whole is kind of a special interval. And basically the whole can never win, because when the whole wins, then this means that you decrease your complexity and then you have a IT. This is something that you can do a couple of examples and work out. So a new induction, which we define R because it's lower. And in theory, I mean, at first you define this induction only for a few combinatorics, not for all of them. So it's not clear a priori that this is well defined. But the point is that you show that an acceleration of this gives you the first one you had before. And this was always well defined. So then even if you only use the few cases to define these, actually, these are only the only case that happen. Okay. And once you have this, then you show that R is well defined. And fits into Fougeron framework. And let me just say one word about this, which is basically you have to show a property which is called quickly escaping, which basically means that somehow it's a way of controlling the distortion of your algorithm. It's something, so it's a property that, for instance, the classical Rosi Vincha induction has. And
so sorry, in the case of the classical, it's exponential states. What is it in the case of the classical?
No. It's still called quickly escaping, but it's something on the you see on the graph. It's basically if you know Kerckhoff paper about unique. Yeah, it's basically the property that Kerckhoff proved there, which is the fact that the size of the interval is always balanced with great probability.
Which at the end of the day is the key point in exponential mixing, though, even though it was not the original proof.
Sure.
Yeah,
exactly.
Sure. I understand.
So this is, I mean, as I said, Charles' work is really beautiful. I encourage you to have a look at it. But he exploits a lot of idea from Stephen Kerckhoff and Arthur Avila, Sébastien Guzel, and Jean-Christophe Yocos. So it comes from there. And then it also has a lot of thermodynamic formalism using techniques from Sárig and things like this. But now I don't want to go into all the details.
But the thermodynamic, the measure mu that you had before is also coming from Fougeron formalism.
Yes, it's coming from there, because basically what it shows is that, I mean, once you have this, what you do is that you look at the suspension of the flow. And then there you can apply thermodynamic formalism. And but let me say that so we don't do it, but one thing that I think is true is that the measure should be the limit of like Lebesgue measure condition on the fact that the thing that the IT is not a finite type after step n. So you can take the set of parameters that tells you that the ITM is not finite type after one iteration, or not after two. I mean, does not stabilize in 2 or 3 or 4 times, right? And this gives you a smaller set of parameters, and then you can take Lebesgue measure there, and you can look at the limit of this. And I think that the limit of, I mean, I'm pretty sure that this is the limit, but we haven't done the exercise or the proof. I don't know, depends. I haven't done it, so I don't know how difficult it is, but we haven't. I'm confident of this. So somehow it's not an abstract measure. That's what I want to say. Okay, I think my time is up. So maybe I will stop here and I'll see what questions. So thank you very much.
Thanks a lot, Mauro. So applause from everybody. So it's time. Actually, we can continue with questions. If there are some more questions in the audience or comment, please. Or on the chat line.
Mauro, in the classical case for usual rotations, you can say something more extreme than just saying, oh, typically you're not weakly mixing. You're at the other end of the spectrum where you have pure point spectrum, right?
Mm-hmm.
Can you say something more precise about the spectral type here, or no?
So we don't look at this. So I mean, okay, let me clarify one thing that maybe I wasn't. So this is somehow this is a corollary. Actually, I don't think it's even written in the paper because this preprint of Trubetskoy came out after, and it's short. It's like 10 pages, but I didn't read it. I didn't read it carefully, so I don't know if he looks at it. I don't think so, but I'm not 100% sure. So, anyways, we don't look at this, and I don't know the answer, so I wouldn't bet on anything. But yeah, it's of course, as I said. So I plan to write some open problems at the end, and also if you look at our paper, there's history of the results at the beginning, and there are some of the questions that we think interesting at the end. So actually, we know very little about this. So there are plenty of open questions, and yeah, this is surely an interesting one.
Thank you.
Other questions?
If you think to generalize it like to something like three rotations, do you expect like just similar results, or do you expect there's something fundamentally differently happening?
So, as I said, there is a conjecture by Boschunitsan and Kornfeld, which tells you that you expect this behavior to happen for all ITMs. So, 3 rotations or whatever you want to consider.
But do you also think from the proof it would be like just similar then to go to 5 intervals, or do you think like there is a thing?
So the problem is that somehow you have to, okay, I think there is hope, but I wouldn't say it's that straightforward, because you see, we needed a Rauzy induction, and the complexity of ITMs grows quite a lot. So it's not that easy to reduce them to IETs somehow.
Okay, so it will just be, I mean, it might be like a combinatorial.
Also the other problem is, as I said a few times, like here is clear, it's crucial the fact that this hole is the size of the overlap.
Okay, and then you get a lot of different holes.
Yeah, exactly. When you get a lot of them, then you get a lot of different holes. I mean, I think you can always do something like this. Just, you have some overlaps, you cut them, but the problem is that then you can have a lot of types, and then it becomes really complicated to define a Rosi induction.
Yeah,
and especially, I mean, one would have to do a lot of examples and try to find a pattern somehow.
Yeah.
And because it could happen that, your Rosi induction is not well defined. So I think it's challenging, but I think there's hope. I think there's hope.
Okay, thank you.
Thank you for your question.
If there are no other questions.
Okay, can I ask one last question? So I remember you had some problems for a long time. So what's the problem in Charles work not being ready? Well, it's difficult to apply Charles work. So how difficult is it to track this?
Well, I mean, it's So yeah, it's true. We worked on this for a long while. Actually, before at the beginning, Charles was not one of us, so that was a problem as well. More seriously, so Charles' work came out halfway through our work, but even after his work came out, it wasn't 100% clear how to define an induction so that this framework could be used by us. And also, you have to be somehow, you have some ideas on how to define this, but then you have to carefully check that you are that this sees all the space you want, so that it's well defined there. And
so I'm sorry, what is the most technical work? Is it also in apply Fougeron?
No. It's to show that you can apply it, which is you have to show that this induction is well defined, and then you have to show that it fits this framework. So you have to show, for instance, that all the letters win with full probability, they lose with full probability. Then some of, not all, but some of the properties that that apply for that. Not apply. What do you say that holds for the classical Rosi induction?
No, I understand. Thanks.
Okay.
Okay. Again, if there are no other questions, maybe yes. No, okay, then we can thanks again, Mauro, for the very nice seminar. So
thank you for coming, for all the questions.